and it gives much more application, you know. So let me start with this definition of matrix multiplication. So given two matrices A and B, where A is AJK, which is M by N matrix, and B is BJK, with N by P matrix. So paying attention to the sign, so you can see that the number of columns of A is the same as number of rows of B, right? And now you can see why we have to require that later. Then the product C equal A multiply B. So you can use a point or without the point, it's okay. We did notice multiplication without point, you know, with or without this dot. In this order is an M by P matrix defined by C containing the entry CJK, M rows and P columns, with the entries now defined as CJK. Look at this definition of CJK. So AJ1 multiply B1K plus AJ2 multiply B2K plus blah blah plus until AJ and BNK. Now, so we can write shortly using the sigma notation, sigma symbol here. So sigma of AJLBLK, L running from 1 to n. This is the notation of the sum now. So this is shorter to use this sigma, so that you don't have to write too many terms here. You just write the sigma of AJL multiply BLK, L running from 1 to n now, where this CJK is defined for all j from 1 to blah blah to m, and for all k from 1 to p. So all the entry of C. Yeah? So again, if you look further, look in more detail, you see that here you have we add product. So here the first factor here is aj1, aj2, blah blah until ajn. So the first factor in every product here are entries of A, of course, and lying on the raised row of A, aj1, aj2, blah blah, ajn are all entries lying on the rows raised, yeah, on the raised row of A. And the second factor here, B1K, B2K, blah blah, BNK, are all lying on case column of D. Yeah, on case column of D, because the second index is K, indicated that this B1K, B2K, blah blah, BNK are entries on the case column. So CJK, it means that we multiply raised row of A to case column of B in this rule. Yeah. So therefore we need exactly on the raised row of A exactly n entries. So AJ1, AJ2, blah blah, AJ1. Therefore A should have n columns. And here on the case column of B, there are exactly n entries, yeah, so that it has enough entry to multiply with the row of A here. Therefore, we require that the number of rows of B is n, the same as the number of columns of A. This is why we need important fact here: the number of columns of A the same as number of rows of B. No? Okay, so we can understand simply and remember simply. So CJK is raised row of A multiply case column of B, so multiply each entry in raised row of A by the corresponding entry in case column of B, and then add this end product. So multiply rows into columns. But let's draw a picture here. Look at this. Here we have A the first matrix and B the second matrix, and the product denoted by C. Then you have the row. If you want to compute the element or the entry of C at raised row and case column, so C sub jk, we have to look at raised row of A and case column of B, and then we multiply raised row of A with case column of B in this way. No? So array 1 be 1k, correspondingly first with first, second with second, third with third, and blah blah, last with last, and then we add this product to obtain C sub jk. Okay, like before I give you an example, I should emphasize again that A multiply B is defined only if the number of columns of A, number n, is equal to the number of rows of B, n. So mn, and then np, and then the product is mp, right? And here I give some example here. So you have here the first matrix A is 3 by 2, so 3 rows and 2 columns. Therefore, the second matrix should have 2 rows. Whatever, no matter number of column of second matrix is, but the number of rows should be must be 2 rows, so that it's the same as number of column here. Therefore, we can multiply. So here you have the C11, so the entry on the first row and first column should be first row multiply first column, so 1 2 4 1, then add. So we obtain this, so we obtain 6. Similarly, the second here, the first row and second columns first multiply second, so 1 multiply 5 plus 4 multiply minus 2 is 1, and blah blah. So going to the second, so the second row and first column, so second row multiply first column, so 2 2 2 1, so we will obtain 6 again. So 4 plus 2 is 6, and blah blah. So you can obtain all. The important thing here is you have to have here the number of columns of the first matrix should be the same as number of rows of the second matrix. There is a mistake here. This entry on the third row and first column, third row first column should be multiply 1, not minus 1. So 3 multiply 2 plus 0 multiply 1, so plus 1, not minus. So you can check whether I made a mistake, and you can correct for me. So in slide I will correct this now and then upload to you. Okay, let me do another computation on the whiteboard so that you can see it in more detail. Right? Where's my whiteboard here? So I clear the canvas. Okay. So let me compute. This here 1 2 minus 1 3 0 4, for example. This is 2 by 3. Let clear it so that it's easy to see. So whatever you have here, you see that you have here number of columns of this matrix A, our matrix A. Number of columns of A is 3. So actually, if you want this matrix that can be multiplied with A in this order, then the number of rows should be 3 here. And number of columns, whatever, but number of rows should be the same as number of columns here, so that it can multiply, can be multiplied. So 3 times, say any number here you like, but let me put by 3, so we'll write 1 0 minus 2 3 1 4 0 1 minus 1, for example 2, for example. This is B. Okay, let me write a little bit more beautiful. So this is what I'm writing here is 2 now. And you obtain a product of these two matrix denoted by C. Before we compute on the entry here, we have to determine what the size of C. So 2 and 3. Number row of C is the same as number of row of A, and number of column of C is the same as number of columns of B. So 2 multiplied 3. Then now we want to find all the entry here. So let's start by C11. So C11 just means the entry on the first row and first column. So it should be obtained by multiplying the first row here and the first column here, right? So it is 1 multiply 1 plus 2 multiply 3 plus minus 1 multiply 0. And you obtain 1 plus 6, 7, right? So therefore you can write here 7. And similarly for this second here, C12, you have to multiply. So here the entry on the first row and second column. So you multiply first row with the second column. So C12, blah blah. Yeah. So I just write here 1 0 0. So 0 plus 2 plus 1. So minus 1 multiply minus 1 is 1. So you obtain 3. So you can write here 3. And going on, yeah, so this so on. So let's write on for me. This is easy. So this is minus. So we obtain here is so first row and last column is we obtain minus 2 plus so we obtain here what is more. So minus 2 plus s minus 2. So we obtain 4. And you can do faster than I because you are younger now. And you can compute faster than me, than mine. And so on. So second here you have 3 plus 0 plus 0. You have 3 here. Am I right? And good. And here you have minus 4. And the last one is minus 6 plus 8 is 2. Am I right? You have to check this. Sometimes I do it fast and I make some mistake. Okay, then we can return to the slide to make some important remarks here. Okay. I return to the slide. Good. Where is this? Okay, then let's see what happens if we interchange the order of this product. Then actually it's not defined anymore, because here if you change this second matrix to the first and the first to the second, then the number of column here is 2, but number of row is 3. So 2 multiply. So here is not the same. The first matrix has 2 columns, but the second matrix has 3 rows. Then the product is not defined anymore. And what is more interesting is I want to give you this example. A equals 0 1 0 0, B equals 1 0 0. So you can multiply AB. So the first row multiply first column 0, plus 0 0. The first row multiply second column 0 0 0. Second row first column 0, second row second column. So you obtain 0 matrix. Now you can write the 0 a little bit bigger than the normal 0 here. Write a little bit bigger. But let's multiply B with A. You obtain this. So let me do the multiplication of B and A. Huh? So that you can see something stranger for matrix multiplication. I write here in the whiteboard. So let's draw. So you have A, which is 1. This is B. Yeah, this is our B. And here you have A, which is on the slide we have, if you write in other orders, A multiplied B is already 0. Actually, in this case, you have AB is 2 by 2, and then it can multiply in both order. Yeah? Because the number of row here always the same number of column here, the same number of row here, number of rows here, number of columns here, the same number of rows. You can multiply in any order because the all of the number of rows and number of columns here are the same. They are 2. Yeah? But let's multiply this. So 1 0 multiply 0 0 obtain 0. 1 0 multiply 0 1 you obtain 1. 0 0. Of course, when you have a 0 rows and you multiply with any column, is again 0 because every term is 0. Yeah? This is different from 0 because at least number 1 is not 0 here. And 0, this is our 0 matrix. Yeah? And this is A multiply B. So you have here B multiply A. What can you say? This means generally you have BA is not AB. And this means that the matrix multiplication generally not commutative. No? This is bad, but not too bad because sometimes the operation is not commutative. For example, what we already saw before is the composition of two mappings. Again, not commutative, no, but it's still associative. This is good enough. It's bad, but it's not too bad because we still work with this. No? Now we return to the slide. So let me return to the slide. Good. So therefore, generally, we can say the matrix multiplication is not commutative. So AB is different from BA in general, even when they are defined. When both products, both orders are defined, generally they are different, as we already saw here. Yeah? So AB is 0, but BA is 1 0 0 1. Should be 1, should be somewhere here. So this is some mistakes. Number 1 should be here, right? Yes, number 1 should be here. This is a mistake, no? So I will check. I will correct this, so you can see on the whiteboard, you know. But they are not 0. Good. But the more important thing that you will see here is normally you have, if you have a numbers For example, A, B are real numbers. Then whenever you have A multiply B, the zero, then it follows that one of the two numbers should be zero. A is zero, B is not zero. But here you see both of A and B are non-zero matrix, but the product is zero matrix. So this means that generally, this is sample already shows that A multiply B doesn't imply one of the two are zero. No, one of the two is zero matrix. It doesn't imply that. So the matrix multiplication is very special. It's not commutative, and the product of two matrices is zero matrix doesn't imply that one of them is zero matrix. It's different from numbers. If you have a product of two numbers which is zero, then you obtain that one of the two numbers has to be zero. Good. So now we are going to the next property. Good. You see here that I list the property here, and you can use when you are working with the exercises. So suppose that we have A, B, C, D. There are matrices such that A, B, C can be multiplied. And K are numbers. So think of few K here as a set of real numbers, so that you don't be worried about K anymore. So let's think of K as a set of real numbers. Because more of the time we are working with real numbers. So then we can, when you multiply K with D, you can put brackets anywhere. So we can put K here and brackets AB, and actually you can put K in any place. KB. What does it mean? When K is a number, then you can put K any position in a series of products. Now you can put K anywhere. It's the same. The proof is easy, of course, because multiplication by a number is scalar multiplication. You multiply K with every entry. So therefore you can draw K anywhere you like. So good. Although a matrix multiplication is not commutative, but luckily enough, it is associative. This is good news, So we can have a structure for that. Operation that is associative. So this is property of associative. This means you can put brackets anywhere, and the result is unchanged. Therefore, we don't have to put brackets with the right ABC, because no matter where you put brackets, the product is the same. Therefore, we don't have to put brackets. And then this property CD, that means the property of distribution, distributive property. So you A plus B multiply C is equal to AC plus BC. Because the multiplication generally is not commutative, so we have to write two property to other hand side, in both orders. So B multiply A plus B, the same as BA plus DB. Of course, all of these four property here, true, provided that the expression on the left hand side are defined. So when it's only one hand side defined, then the other hand side, of course, also defined. And they are the same. Good. We don't have to prove this. This is long. It's easy, but it's long. We don't have to waste the time for that proof. Use a property. So let me perform a property here, so that you can see if sometimes if we can apply the properties, and the computation is easier, simpler. So let me show you an example that using the property here. or whatever you have. I give you here the whiteboard where what is okay. Let me look. Where is my whiteboard? Okay, it's here already. And I share the white. Good. I clear the canvas. Okay, suppose that I have A equal minus 1, 2, 3, 1, and B equal 1, minus 2, minus 3, 0, for example. Um, better. So 2, for example, this is B, and C, whatever C, so 2, 1, minus 4, 3, for example, no? And let's compute AC plus BC. So if you compute readily, A multiply C, and then B multiply C, and then you add, then it's a little bit long. So as the first step, we write as A plus B, because we know that property or product of matrix multiplication is distributive, so it means that we can put C as common factor, but it should be in the right order here. No? If here AC, then should be BC here, so that you can put C outside. No? And then you can add A with B first, so you obtain 0, 0, 1, 3. Then it's simpler because here you have money 0. No? So the product will be easy when we have many zeros. So 0, this of course 0, 0, that of course 0, and this is so you obtain 2 minus 12, so you obtain minus 10, and here you have 10. Good. Is this shorter a little bit? No. Good. So this is an example that sometimes you can use the property so that our computation is simpler, right? As you are computing directly, then maybe it is more complicated, it's longer. Good. So I am returning to the slide. Good. And I want to give you some special matrices. The names of the matrix when it has some special property, then we will give it some special name. You know? Good. So first thing I want to introduce here to you the triangular matrices. Now there are two kinds of triangular matrices. The first kind I want to give it here. A square matrix is called lower triangular even only all of its entry above the main diagonal are 0. So you have if the matrix is square, then you have a main diagonal now. And if all the entry of this matrix above the main diagonal are 0, then we call it the lower triangular. Why is this? Because the upper part, this means so all the entry about the main diagonal are 0, means that the upper part of the matrix contain only 0, and the information, the important information, if any, lying in the lower part. Now this is why we call this lower triangular, and we call this upper triangular if and only if all the entry below the main diagonal are 0. And then if it is either lower triangular or upper triangular, you have the common name, and the common name is triangular. So the matrix is called triangular matrix if and only if either it is lower triangular or upper triangular. Good, let's give you some example now. But before doing that, let's write a little bit generally. So let's consider n square. N square means that n by n matrix, yeah, AJK. So it is a lower triangular matrix if and only if AJK is 0 for all j less than k. So when the first index less than the second index means that the entry uh, above the main diagonal. Đó. Um, and it is called an upper triangular matrix. You can only if AJK 0 for all j greater than k. Đó. This is corresponding to the lower part when the row index greater than the column index, then the entry are lying on the lower part. No, and if the lower part is 0, then the matrix is called upper triangular matrix, because all important information if exists lying on the upper part. The lower part already 0. Here you can see this is lower triangular matrix because the upper part 0, right? So all the entry above the main diagonal here are 0. No? And here is the upper triangular because all the entry in the lower part of the matrix is 0, are 0. And both of them are called triangular matrix. Either it is lower or upper. We call it the common name triangular matrix. Okay, now we go to some more special matrices. Yeah? Now this is now we go to the diagonal and unit or identity matrices. So you have here a definition of diagonal matrix first. So an n square means that n by n, you know? N rows and n columns, the number of rows and number of columns are the same. So we call it square. And the number n denotes the number of rows or columns. You know? So an n square matrix is called diagonal matrix if and only if all of entries outside the main diagonal are 0. So AJK, when j is not k, means that AJK is not on the main diagonal. No? So this means diagonal matrix if and only if all the entries outside the main diagonal are 0. This means the important information, if any, lying on the main diagonal, because outside the main diagonal is 0. No? And it's called the square matrix is called units or identity matrix if and only if it is diagonal matrix, because it's 0 if j is not k. And on the main diagonal means that when j equal k, the entry is 1. So the multiplicative identity in the field k is number 1, because our k is real numbers or complex number is still 1. So let's think about 1 so that it's simple to understand. Just number 1 here. Yeah. So this means that units matrix or identity matrix is simply a diagonal matrix, and on the main diagonal all the entries are 1 here. You know? So outside the diagonal the entries are all 0, and on the main diagonal the entries are all 1. We denote the n by n units or identity matrix by I sub n or simply by I if n is clearly understood. Now let me give you here. So this is diagonal matrix because outside the main diagonal all the entries are 0. No? And this is units matrix or identity matrix when it is diagonal matrix, of course, and on the main diagonal all of entries are 1, right? Good. And now let me tell you why this is called identity, because let me show you on the whiteboard. Uh, so let me consider A, which is m by n matrix. That is to say, A belong to m by n in K. So this set m by n K means that the set of all m by n matrices with the entries belonging to K. Yeah? But our K is simply R. Let's think about the set of real numbers R, because most of the time we are working with R. Sometimes, very rarely, we are working with C, but most of the time we are working with R. So let's think of K as R, and don't worry about K anymore. Let's think of as set of real numbers. And then can you tell me if I have an identity or unit matrix and I want to multiply with A, tell me what the sign of I here. Can you tell me what should I write here? What the sign of I? Who can say that? It's easy, right? So I here is square matrix, number of rows and number of columns is also the same, and I denote by only one letter. And what letter should I write here?
M multiply N.
M, yeah, because this is number of rows and number of columns of I, and it should be the same as number of rows of A, right? So this should be M, and let's do this computation. Yeah. Let me, for example, let me take 1 0. This is the first row of IM. Multiply the first column of A1 1, A2 1, blah blah, A M 1. So you see, it should have here enough M elements. So I M, no? What do you obtain? This is A1 1 because the other is 0, no? And if you multiply with the second row, a second column, so a 1 2, a 2 2, a m2, you again you obtain a, this is a 1 1, you obtain a, so 1 multiply 1 2 is a 1 2, and the other is 0 0 0 0, you know, so the only remain is a 1 1, and blah blah until the last one, a 1 and a mn. So you obtain here only way 1 1 remain, and the same for the other, you know. Uh, so actually this is equal to A, right? Um, and similarly, you can okay, I write a little bit nicer. This would be here. This would be a 1 n. That should be as matrix, and this matrix that's equal. Yeah, this is A. This is I m. A equal A. Yeah. Similarly, you can multiply A with I, but the other side here should be n. Yeah. Number of columns of A should be the same as number of rows of I, so here should be in. And the name identity is clear when we consider m equal n. Yeah, then we don't have to, because then m equal n, this means a belong to m n by n. Okay, then we can write a I, because a now n by n, and a also n by n, so the n now is clearly understood. There is only one n here, so we don't have to write n here anymore. No? And therefore this I plays the role exactly as multiplicative identity. You know, I multiply a equal a multiply I equal a. So why? So this is the name identity coming from. You know? Therefore we write. So this is the name identity. This means the neutral element corresponding to the multiplication. Yeah, our unit matrix. So, and I want to ask you the following question before we are going to further computation. Um, so now let me notice shortly. Okay. So the first remark, exactly as what I already wrote in the whiteboard. No. So a multiply in equal a equal im multiply a. This is what I already wrote in the whiteboard. And secondly, in case m equal n, we have another notation, another notion. So we denote by mn k equal the m n by n, because now m equal n, so there's no need to write two same letters here. So I just write one represent n by n. So instead of writing n by n, we write only n here. So we denote m n k equal this m n by n. Then you can see immediately that m and k with addition, so matrix addition, and matrix multiplication. In this case, the matrix multiplication is well defined on this mn, because every two matrices here can be multiplied because they have the same row and same columns, and you can multiply in any order. So this matrix multiplication now a binary operation on this m and k, right? Now we can check this m and k addition and multiplication is a ring, but of course it's non-commutative, because here you have multiplication is generally non-commutative. It's not commutative, So let me check. So we already had unit, so identity, when n equal n, so you have ai equal ia. So I is multiplicative identity, of course. And now we check the other, but we don't have to check because I already list property here. You see. So the, of course, m and k with addition is clearly as previously we already had that structure m and with addition clearly a commutative group. Now with the addition is no problem. It's the same as the real numbers. And you have the multiplicative is associative, and there is identity, multiplicative identity. Good. And this is a two property of distributive is true, and therefore you obtain that this is a ring, but it's non-commutative ring. Again, you see that we do not have a good operation for multiplication, but it is good enough, because it's from a structure of ring. So we can compute the same as we are in the set of real numbers of integer, because the set of integers is also a ring. But pay attention that this ring is not commutative. I will do some computation in the ring. After we have a short break. Okay, now we have a 10 minutes break, and we resume after 10 minutes. Okay, have a short break. Okay, we continue. Um, of course, I want, as I said before, I want to do some computation, on this string. Um, and so just want to tell you that you have to pay attention, to some point when you compute in this string. So let me return to this whiteboard. Good. So you have here. So suppose we have m and k. So let's think about k as set of real numbers r. So don't worry about k, because more of the time we are working with r. So let's think of k as r, and addition and matrix multiplication. So we use this non-commutative, rings. And now so we can compute as we are in the set of integers z, but for the set of integer we have a property of commutative, but here we do not have that property, so generally ab is not ba, generally, therefore, for example, if you compute ab square, then it is a plus b multiply a plus b. Then you can compute a multiply, because it has property of a ring, so you can multiply it out, this distributive property. So ab, but then you have ba b square. Now you cannot write ab plus ba as 2ab anymore, because generally ab is not ba, so you just let it be in this way, so no hope. If sometime you have AB equal BA, then you can write 2BA, but generally you cannot write 2BA. Just let it be in that way. But one more computation. Normally you have here A square minus AB plus BA minus B square. But actually, if AB equal BA, then you have minus AB plus BA are 0. But here generally is not 0. So generally you have, this is different from a square minus b square. But if sometimes, if you are lucky, if we are lucky, sometimes if we are lucky, we have some couple of matrices that are commutative. Sometimes that happen. For example, if you have I multiply A, some way A multiply I, sometimes, then it follows that you obtain a, because now you have this minus AB plus BA are 0, so you obtain AB multiply A plus B multiply A minus B is A square minus B square. It's true only in case that AB equal BA, but generally it's not, because generally they are different, so generally not equal. This is what you have to pay attention when you are working with matrix multiplication. It's not commutative in general. Good. Okay, we return to the the slide again, and I want to give you some more names, some more special matrices. We are going to the symmetric and anti-symmetric matrices. So a matrix A is called symmetric if and only if AT equal A. So the transposition of A equal A is shown. No? And it is called skew symmetric or anti-symmetric. So there are two names for this. Yeah, you can call skew symmetric or anti-symmetric if and only if AT equal minus A. So what does it mean? Let's pay attention more in more detail. You have AT. So AT is just obtained from A by writing a row of writing row of A as column of AT correspondingly. No? First row turning to first column of AT, second row of A turning to the second columns of AT, and blah blah until the last. Good. What does this mean? This means if you have A equal to JK, a JK is element of raised row and case column of A. Then when you transpose AT, a JK become a KJ. But these are two matrix are the same, so these two entries should be the same. No? So this means A equal to JK is symmetric if and only if a JK equal to KJ for all JK running from 1 to n. No? So in this set of index. And similarly, this is a JK and by n is skew symmetric if and only if AT equal minus A. This means after you take transposition, it's become minus A. This means the entry as raised row case column and the entry of k rows and raised columns should be opposite, so that when we exchange, we obtain the minus sign. No? So let me show you some an example so that you can see. So this is symmetric matrix because you have here. So we don't care the main diagonal because on the main diagonal actually is stay unchanged. So AJJ is AJJ. You know? Because when we take the transposition, the entries on the main diagonal stay unchanged. Yeah, don't worry this. But this A1 2, this is minus 3, is in matrix AT is become a 2 1. Therefore, these are two entries to be the same, so that when you take transposition, you obtain the same matrix. So this A1 2 should be the same as A2 1. So minus 3 minus 3. Similarly, A1 3 is the same as A3 2 3 1. This here A2 3 should be the same as A3 2. So what does it mean? It means that the entries that are symmetric across this main diagonal should be the same. Yeah. So here these are two entries are symmetric across this main diagonal. Of course, are the same. And here 2 and 2 here of course symmetric across this main diagonal. Then they are the same. 0 0 here symmetric across this main diagonal, right? And similarly for skew symmetric, but now we do not have equality, but we have the opposition. Yeah? But let's see the case that when J equal K for the skew symmetric, then immediately we recognize that on the main diagonal of a skew symmetric matrix, we have a JJ equal minus a JJ. Therefore, it should be you turn to the one side, you obtain 2 AJJ equal 0. Therefore, AJJ is 0. Then for skew symmetric, it is clear that on the main diagonal it should be 0. And here you see when you have two symmetric entry here should have opposite sign, because when you take AT, the you obtain minus. So therefore, the 2 and 3 here should be opposite side. No? So that minus of minus 3 should be 3. So this is a skew symmetric matrix, and you see very clear that on the main diagonal there are 0 on all the entries on the main diagonal are 0, and if two entries symmetric across this main diagonal, of course opposite each other. Here 3, here minus 3, so a 1 2 is minus of a 2 1. Yeah? A 1 3 is minus of a 3 1. A 2 3 is minus of a 3 2. Yeah? So it satisfies this. Good. This is notion of symmetric and skew symmetric. And what I want to give you here is a remark. The first remark is clearly, because when you take transposition of A and then again transposition, then you do nothing, because A is the column of 80 is simply the row of A, and then you take the column to the row, then again you obtain the row of A. So transposition of transposition is nothing, is the original matrix. So AT and then T, clearly you obtain A is clear now. So you write row as column and then write column as row, then you obtain a row, that row again exactly. So AT and then T, you obtain A. Good. But the second remark is interesting. I will tell you the remark. Every square matrix can be written as a sum of a symmetric matrix and a skew symmetric one. Yeah, it seems interesting. So you can decompose a square matrix as a sum of symmetric matrix and a skew symmetric matrix. How to prove that? So if you already did exercise is number 3, then there is a similar exercise, at the bottom of the sheet 3. But I don't know whether you already did this or not. I will show this here. It's interesting, and it's funny. So let's return to the whiteboard. Let me share the whiteboard here. Good. So I want to remind the property of the transposition before I prove that. Now this seems nice. So what we have to do is to use the property of transposition, but I want to remind you, So remind, if you take the transposition of a sum, this is what we learned last week, then it's equal to the sum of transposition. And if you take transposition of a scalar multiplication, so lambda is numbers, transposition, then it is, you can draw lambda out, because these are two properties that we will use to prove the fact that any square matrix. So what we want to do is, so for square matrix A, we can write A as the sum of C plus D, where C is a symmetric matrix and D is skew or anti, symmetric. How to do this? So let's remember what you already did in high school. If you have a function, this is for function f x defined on symmetric interval from minus a to a, for example, then there were very interesting exercise in high school that we can write fx as a sum of an even function plus an odd function. Do you remember that exercises? As follow. So you should write 1/2 of fx plus f minus x plus 1/2 of fx minus f minus x. Yeah, this is for f minus x. You obtain here plus here minus, so it's disappearing. The remaining is 1/2 fx plus 1/2 fx. It's clear fx. But you can easily check this function is even function, and this function is odd function. Yeah. So this means every functions that are defined on a symmetric interval can be written as a sum of an even function and an odd function. So we do similar thing here. We write 1/2 of something. So a plus at, and then plus 1/2 of a minus at. Right, and then here you have minus, you have 1/2 80, and here you have minus 1/2 80. So 80 disappears, so the only remain is 1/2 a plus 1/2 a. So we obtain a clearly. Right, good. Now we put this matrix by C and this matrix by D and prove that C symmetric and D is skew symmetric. Yeah, and we are done. So to do this, let's take the transposition of C. So CT. This means you take the transposition of 1/2 of A plus AT and then T. Yeah. Now you apply this property lambda A to a transposition. You can draw lambda out, so we obtain 1/2 out. So A plus AT and then T. So I have to delete that part here so that we have more spaces, right? Then you have 1/2. Now again apply this property here. The transposition of the sum is the sum of transposition. But look at the properties that I gave you in the slide. Yeah, this is AT and then T, you obtain A again. So 1/2 AT plus A. But this is again C because the addition is commutative. So you have A plus AT, the same as AT plus A. It's clear, right? So this means C is symmetric. So this follows that C is symmetric. But now let's consider D. And we have to prove that dt equal minus D. So let's compute the D of transposition of D. So we have 1/2 A minus AT, and then all of them take the transposition. But again, using this property, you can draw 1/2 out, and the inside would be A minus AT, and then T. And now again, you use this property. So transposition of the sum and the sum of transposition, and minus can be drawn out. So immediately you obtain 1/2 80 minus 80 and then t. But this is 1/2 of 80. So 80 and then t again you obtain a. Okay, now I have to delete that part here. It's nice representation, right? It's very nice representation that you learn in high school. And we use that idea to continue with this decomposition here. Good. Now you have this is just minus of 1/2 a minus 80, because minus that means we multiply with minus 1, you know? Multiply with minus 1, here you obtain minus 1/2 a, and here minus 1 multiply minus 1 you obtain 1/2 80, so you obtain that. But this is exactly minus of d, so what you obtain is dt equal minus d. So therefore you follow that the skew symmetric, yeah. So we obtain what we want to see, QED. So A can be written as a sum of C plus D, where C is symmetric matrix and D is skew symmetric. Yeah, it's nice, yeah, and funny, right? And the idea is actually similar to the idea when we worked in high school, you know, with the a function that is defined there on a symmetric interval that can be decomposed as a sum of odd even and even odd function and even function. Yeah. Okay, we'll return to the slide and give you. I want to give you the last property related to transposition here. So you take transposition of product, then you can prove that easily, but long. So I don't prove this now. So A multiply B and then transposition is equal to BT multiply AT. Provided that AB is defined and BT and AT is defined, yeah, then they are equal. We can say shortly a transposition of a product is product of transposition but in reverse order. So you see the order here should be reversed, yeah. BT80, so ABT equal BT80. So we will use it later, yeah. Now we go to the first application of the matrix multiplication, yeah, which is application to system of linear equation. So you can see here I give you definition of system of linear equation. Actually, in high school, you already had or you already learned some version, some simple version of that system, you know? And now we go to general model, you know? General form of system of M linear equation in n unknown x1, x sub 2, blah blah, x sub n. So this system is simply a set of equations that occurs at the same time. So we use the notation n here to indicate that these equations satisfy at the same time. No? The first is a11 x1 plus a12 x sub 2 blah blah until a1n x sub n equal b1 and blah blah until the nth equation has the form a m1 x1 plus a m2 x sub 2 blah blah plus a mn x sub n equal bn. Here a jk this means a 1 blah blah until a mn are given. So yeah, and b1 b2 bm also given. So I write here so that you can have say short notion here, no? So a jk's are given numbers in a few case, but let's consider the real number, for example. No? Of course, you can consider in any field, but let's think about real numbers so that it's easy for you to understand what going next. You know? Uh, and these numbers AJK are called the coefficients of the system. They are given, and the unknowns are this x1, x sub 2, blah blah, x sub n, which we have to find. These are unknowns. You know? And the number b1, b2, blah b blah blah until bn is also known, also given. And here I give you another name. Normally we call this system 5.1 is system of linear equation, but sometimes we can call it linear system of equation. It has the same meaning. Yeah? And the next time we have some more names depend on the right hand side here, b1, b2 to bn. If the right hand side are all 0, so if bi equals 0 for all I running from 1 to n, this means all of them are 0, then this system 5.1 is called homogeneous system. And if it's not the case, this means that at least one of the b, so say at least bk, at least one bk is not 0. No? At least one of them is not 0. This means it's not homogeneous system. Then we call it non-homogeneous system. Non-homogeneous means that not homogeneous, you know, because at least one of them of the right hand side here is not 0. Good. And now I give some notation such as solution, yeah, and the other here. A solution to this system 5.1 is simply a set of order numbers x1, x2, blah blah, xn that satisfy only the m equation at the same time. In this 5.1, we have numbers and we put to this equation and we obtain identically true, something identically true. Then we call the solution. And if we arrange it in a column, if we arrange solutions in the column, then we obtain the solution vector. So solution vector of 5.1 is this column x from x1, x2, blah blah to xn, whose components are constituting a solution to this 5.1. And one very special remark that if the system is it's homogeneous. Yeah? The homogeneous means that the right hand side is 0 ohm, then actually it always has 0 as solution. All of them are 0. So x1 is 0, x2 is 0, blah blah, xn is 0. So here you put all of x1, x2, blah blah to xn are 0, then you obtain the right hand side here 0. Well, the right hand side always 0 is corresponding to the homogeneous system. So actually, this means that okay, sorry for disturbance. So it's clear that if the system is homogeneous, then its own way has trivial solutions. This solution that all of the unknowns are 0 is called trivial solution. Yeah? And next time, now we want to write the system 5.1 as a matrix form, so that we can apply the operation that we had before to the case of system of linear equation. So with this purpose, let me return to the whiteboard to show you Actually, this is we can write as a matrix form. Where is this? Okay, so let me write the first equation. Yeah, you see the left hand side of the first equation is a11 x1 plus a12 x sub 2 blah blah until a1 n x sub 1 n. Actually, this can be written as uh, the row a11 a12 blah blah until a1 n multiply our column x x1 x sub 2 blah blah x sub n. Can you see that you should multiply this row with column, you obtain this here clearly, no? And the second equation in the same manner you can obtain uh, what is this? This is not a1 2 anymore, it should be a 2 1, yeah, x1 plus a 2 2 x sub 2 blah blah until a 2n x sub n. This is again you have the second rows a 2 1 a 2 2 blah blah until a 2n, and then multiply with the same column vector here, you obtain this part here, yeah, and blah blah until the last equation, the last left hand side of the equation, a m1 x1 plus a m2 x sub 2 blah blah until a mn x sub n. Actually it is the same as the last row, a m1 a m2 blah blah until a mn. Multiply this column, and actually if you multiply the first equation, actually you obtain b1. So this element here you obtain b1, a second element you obtain b2 blah blah until the end you obtain bn, right? So that set of equation, this means that you multiply a matrix with a column, so this is a m n, no? And you obtain correspondingly component of the other columns, no? It's exactly by the equality in matrices. So therefore I am telling you now the matrix form that we put. This is a, which is ajk, and this is x, so we obtain a multiply x, and this is b equal b. And this is exactly that what I want to tell you now. So here what I want to tell you now is this slide. So coefficient and augmented matrix, as you saw in whiteboard, we can read we can write system 5.1 in the matrix form ax equal b, where a is actually a jk, as I already wrote in the whiteboard, and this matrix is called coefficient matrix of the system 5.1. And this x, actually this is a vector of unknowns, or solution vector if you like, but sometimes there is no solution, so like cone is vector of unknowns is better, no? So vector of unknowns, and b the right hand side, so with the cone is the right hand column vector, yeah? So what we want to do is to find this x, this unknown, So the vector of unknowns, or you can call solution vector, because what we want to find is x. Yeah. And good. Then we have the following notion, a theorem, which is defined by writing column B on the right hand side of the matrix A. Yeah. And you use a very thick, a very thin slash here. You can write or you don't have to write. It's just I write this slash here just for you to distinguish between two blocks here. The first block is matrix A and the second block is column B. Yeah? And this matrix A theorem is called the augmented matrix of the system 5.1. So it is obtained by the writing column B on the right hand side of A. So you use this slash or not, it's no problem, you can omit. But at the beginning, I should write this slash so that you can distinguish the two blocks here. Now, A and the column B here. So augmented means that make something bigger. So enlarge something. You know? So this is called augmented matrix. And of course, this matrix, I tuner determine the system 5.1 completely, because it contains all the information on the given numbers appearing in 5.1. You know? So the A is the right hand side. And now we will give you fundamental methods for solving this 5.1. The method, as the name is Gauss elimination method. So this is a German name. German mathematicians very famous. This is read as Gauss. You have to read in German way Gauss, no? Gauss elimination method, which is a fundamental method that help you to solve 5.1 just using operation on row of augmented matrix. But let's start by an example from application in electric circuits. Now let me consider this simple electric circuit is contained two loops, you know, the right loop, the left loop, and the right loop, and you have some resistor here, and you have two force sources. We call electromotive force, you know, or you can call simply sources. And now here the resistance here are given, and we have to find the currents, and let's choose the current, choose the direction of current arbitrarily, and so yeah, it's no problem which directions that the current have, because at the end if you obtain the minus some negatives, and this means that the direction is just opposite to what we chose, what we choose, yeah, what we chose. So let's choose direction of this current arbitrarily, but we need some law to write out the equation for that electric circuit. The law we knew in high school already. This is physics in high school, and the law is we have two laws. Actually, we have three laws, but it's important is these two laws. And so you have KCL. So the Kirchhoff laws. The first Kirchhoff law is Kirchhoff current law. So KCL means that Kirchhoff current law, telling you that at any node of a circuit, the sum of the inflowing currents equals the sum of outflowing currents. No? So later on we will apply this law to our circuits. And secondly, we have Kirchhoff voltage law. So KVL, Kirchhoff's voltage law, telling you that in any closed loop, So the algebraic sum of voltage drops equal to 0. Another way to say the sum of all voltage drops equals the impressed electromotive force, the source. Now, okay, with these two laws, we will write the equation, yeah, and then we show the system to find the currents in the loops in the circuits. Good. So let's return to that. So applying Kirchhoff current law KCL and Kirchhoff voltage law KVL, starting by KCL. So on the node P, you have here you have inflowing currents are I1 and I3, and outflow is I2. So we obtain I1 plus I3 is coming in, so the size plus, and is outflowing is I2, so it's to be minus. You can write I2 on the other hand side, and you turn to here, this becomes minus here. No? This is a node P. This is KCL for P, so Kirchhoff current laws. Now the inflowing current, the sum of inflowing currents is the same as the sum of outflowing currents. And now go into the Q. You have node Q. So the here you have the outflowing is I1 and I3, and inflowing is I2. So we obtain minus I1 plus I2 minus I3 equals 0. This is two nodes. We have two nodes here, and then we have two loops. Yeah, the right loop and the left loop. So let's start by the right loop. So you have the sum of electromotive, the sum of voltage drops are equal to electromotive force. You know? So and we have to apply the Ohm law here. So one more law. You know? So Ohm law saying that the voltage drop across a resistor is proportional with the current. Yeah? So voltage drop across this resistor is 10 multiplied I3, and because this is again I3, so we obtain this 15 multiplied I3, and then you have here I2, so 10 multiplied I2, so we obtain 10 multiplied I2 plus 25, 10 plus 15 is 25, I3 equal to electromotive force here, so 90. Here again we apply one more law, which is Ohm law, telling you that the voltage drop across a resistor is proportional with the current. So R multiply I, so it's equal to resistance multiply current. And then the left loop you have here is again you have here voltage drop across the 10 ohm, simply 10 multiply I2, and then across this is 20 ohm, this is 20 multiply I1, so we obtain 20 I1 plus 10 I2 is electromotive force. Here is 80 volts. No? Good. So what we will have here is we rewrite the system in our notation. So x1 is y1, x2 is y2. So I putting x1 is y1, x sub 2 is y sub 2, x sub 3 is y sub 3. We obtain the system, exactly the system that we already saw generally before. Now it's become concretely. So it has 1, 2, 3, 4 equations and 1, 2, 3 unknowns that we have to find. We denoted by sig1. So of course this is very simple system. We can solve by inspection. That means we can solve by substitution. For example, you can draw this x2 here and then draw x3 here and substitute to the first equation, and you can solve it easily. But this is not our case. This is not our purpose to show that. But our purpose is to give you a general method which is called Gauss elimination method, that help you not only to solve this system sig1, but also to solve any other system, yeah, any other general system. You can use that Gauss elimination method. But let's start by easy one so that you can get the principle, you can get the idea, you can get the method, you can look at the easy sample, and then you can apply to every other system. Yeah? And the important thing here is you can see some very important operations that allow you to work not only with system but also with other objects like vector space that we learn later. Good. Now we have the following things. The idea of Gauss is um, so. Firstly, we write down augmented matrix A tuning. Now, this is the matrix A, the coefficient matrix, and then the right hand side, the column B is written on the right hand side of this coefficient matrix A. Now, so we obtain the augmented matrix, and here you have a system, and you see that the idea of Gauss is instead of working with system with too many variables, we are working with augmented matrix contain only numbers, no? Contain coefficient of the system. This means it's contain only numbers. So instead of working with both number and variables, we are now working only with numbers, and this is simpler, you know. So let's see how we can work only with number, but it still work. So let's eliminate. So we want to reduce, you know, to reduce to some simpler system. If we can reduce augmented matrix so that we preserve the set of solution, then we can reduce the augmented matrix in a simpler form, and then it's equivalent to the original system, and then we can show the simple system to obtain the solution, because the set of solution is not changed. So let's see how to do this. Okay, actually look at the system first. We want to eliminate x1, 20 x1 here. So we choose this x1 as a pivot. So this word read as pivot, not pivot. Now you have to read pivot. You can check your pronunciation. So let's choose pivot. Um, and then use this to eliminate the other. So actually we want to eliminate this. So we just add the second equation with the first equation. Correspondingly, we add the second row of this matrix with the first row. So immediately you obtain 0 here. So this means we eliminate the coefficient, and correspondingly you eliminate x minus x1 here. And then if we want to eliminate this 20 x sub 1, so you just multiply the first row with minus 20 and add to the fourth row. This means the row 4 minus 20 multiply row 1, replacing to the row 4, the last one here, minus 20 multiply the first row, so that you obtain here 0, because 20 minus 20 is 0. But we have to do with the whole rows, because it's corresponding to what we do with the equation here. But instead of doing on the equation with many variables, we are doing only on matrix we contain only numbers, and this is simpler, but the result are the same. The result is a new coefficient, and the new matrix here corresponding to the new system of linear equation, and the new system are equivalent to the first one, because what we are doing here is that we adding equation together, or after multiply some non-zero constants, and you obtain equivalent system. It doesn't change the set of solution, because you can easily go backwardly from that system to the original system. Yeah? And up, we are arriving at this new augmented matrix and at this new system, and they are equivalent to the previous system. And now we want to eliminate x sub 2 so that we obtain much simpler until you can show this. Yeah? But if you choose 0 as a pivot, then it's not is impossible, because it's already 0. You cannot use 0 to eliminate any other, because it's already 0. So we have to change this row, put it to the last, to the bottom of the matrix, and we push the other rows of the third row and the fourth row one step up. Yeah? So put it up one step, put the 0 row to the bottom, and put the other row one place up. Here exactly what we are doing. We have to change the order so that we obtain something non-zero, so that we can play it as a pivot. Yeah? To do this, we put the second equation, this means the row of 0 row, at the end, and move the third and the fourth equation one place up. It doesn't change the set of solution. Good. The result is the following. So after you put 0 to the bottom and place and move the other equation or the other row one place up, you obtain this new equation and new augmented matrix corresponding to that system. Now this 10x0 is already 10 multiplied x sub 2 is already non-zero, the number 10 here. You know? So you can use it as pivot, and to eliminate this. You know? Tell me, how can we eliminate this? This is very simple. You know? You just multiply minus 3 with this equation and add it here, so that you obtain minus 30 plus 30 is 0. This is exactly what I want to do here. So for the matrix, now, instead of doing with the equation, we are working with matrices, so that we have to work only with number, not with variable anymore. So row 3 here minus 3 multiply row 2. Why 3? Because 3 here multiply 10 is 30, and then minus is equal to 0. So row 3 minus 3 multiply row 2, so we obtain 0 here, and the other come as a result here. This actually, it means that we multiply the second equation with minus 3 and add to the third equation, and we obtain a simple form of a matrix and then simple form of system. Actually, what we are doing here is we work with only with matrix, and then we rewrite for the system, because we know that this is equivalent. Yeah? Because what one we are doing, the only change is the coefficient, and the variables stay always unchanged. Yeah? So after you obtain a new matrix, and you can write a new system. Yeah? So you don't have to compute in the system. You have to compute only on the matrix, and at the end you write system corresponding to the matrix, right? Okay, now it is already some kind of triangular form, right? And now we can show this, but let's start from easy one. Yeah, so here is the last equation, so just forget the zero equation. Yeah, so just forget zero equation, because zero equation play nothing. So let's start by easy one, so it's lying on the bottom here. Yeah? So we can immediately solve x3. Yeah? And after we obtain x3, we can substitute to the above equation. to obtain x2, and then after obtaining x2 and x sub 3, we substitute to the first equation to obtain x1. All right, so this is called back substitution. Back substitution means that we start with the lowest equation, with the simple equation, as a forget the zero equation, and then we work backward from the last to the first, gradually, of that triangular system. So we readily find x3 and then x2 and then x1. Actually what we do is this way. So let's start by the last one, the easiest one, to obtain x3, and this is i3 as we put before, and we obtain this 2 ampere, because the unit of the current is ampere, no? And then you obtain substitute x3 equal 2. Here you obtain x sub 2 equal 4 with the units ampere, and substituting x sub 2 x sub 3, here you obtain x sub 1. Đó. So we obtain 2. So the system has unique solution. Yeah, x1 is 2, x2 is 4, and x3 is 2, corresponding to i1, i2, i3. Although it has more equations than unknown, but one equation is consequent of the other. No? So still it has unique solution. And here you already have some feeling how we are working with the Gauss elimination. Actually what we are doing is we are doing only on the matrix, and at the end we obtain the simple matrix, some kind of triangular form. Then we write out the system, when we know the system is equivalent to the original system. So we just show by back substitution. And now let's give you some names. So our system, as we have here, it has more equations. So it has 4 equations but only 3 unknowns. So such kind of system is called overdetermined. Yeah, so the system 5.1 is called overdetermined if it has more equations than unknowns. If the number of equations and the number of unknowns are the same, so m equal n, then we call 5.1 is determined. So if m equal n, then system 5.1 is called determined. And if the last case is if it has fewer equations than unknowns, then we call it underdetermined. Good. Now I give you now an example. We already have example for overdetermined, and most of our system will be determined when the number of unknowns are the same as the number of equations. But now I want to give you sample of underdetermined. Yeah. So let's consider this example. It has a system of linear equations. It has 1, 2, 3 equations. But how many unknowns are there? So 1, 2, 3, 4 unknowns. Yeah. So let's work by the Gauss elimination method. This means we write out the augmented matrix. Now I just compute with augmented matrix, and I don't have to write the system anymore, because we know that all of our operation on the row of a matrix is corresponding to the operation of equation on the system. And for example, we multiply an equation by non-zero constant and add it to the other equation. This doesn't change the set of solutions, so we obtain a new equivalent system. But I don't care about system, I care only about matrices. So we do just by computing on the matrices here, eliminates on the matrix, so that you obtain some kind of a rectangular of what a triangular, you know, some kind, you know, of triangular matrices. So if you want to eliminate 6, you know, then you have to take the row 2 multiply with minus 2 and add to this. This is, you can say that this row 2. So R mean row, no? Row 2 minus 2 multiply row 1. This means that you multiply row 1 by minus 2 and then you add to the row 2 and then replace into row 2. Or you obtain. So minus 2 multiply 3 is minus 6. So we obtain 6 minus 6 is 0. So here 15 minus 4 is 11. 15 minus 4 is 11 and minus 54 plus 10 is minus 11. So 25 minus 16 is 11. And here if you want to eliminate this 12, so you have to take row 3 minus 4 row, multiply row 1, so that 12 minus 12 0. So row 3 minus 4 multiply row 1 replacing to row 3. So you obtain 0 here, and then here minus 4 multiplies this, you obtain minus 11, minus 11, 44, minus 11 again. Okay, now you just add to eliminate this here, so that you obtain some kind of triangular matrix. So you obtain, you just add this row. Remember, you have to do operation on the whole row because it's corresponding to the action on the whole equation of the system, yeah, of the system. So let's do row operation on the whole row. So row 3 plus row 2 and replacing the row 3. So we obtain is 0, 0, 0, 0. Ah, we are lucky. But pay attention to the own element, own entries in the row 2 here contain 11 as common factor. So we can divide. Huh? This is the corresponding to the action on the equation that you multiply both sizes of equation by 1 over 11 and replace to those 2. So we obtain simple coefficient here. And now you obtain the matrix are simple enough, then you can write down the system. Yeah? And we know that the system, this simple system are equivalent to the previous system, because what we are doing here is the algebraic sum of equation, but instead of doing on equation, we are working only on matrices. And this is nice because on matrices we have only numbers. No, we are working with number and operation on rows, and this is very nice, very elegant. Good. Okay, now we have this simple, but now we do substitution. Yeah, after you obtain simple equation, now we do substitution. So let's start by the last one. So x2, because here you have redundant x3, x4, you can choose x3, x4, any value, and then you show x2 with respect to x3, x4. So this means you just apply x3, x4 arbitrary value. So x2, and then you solve for x2 equal 1 minus x3 plus 4x4, and then you solve for x1 by substituting x2 to the first equation, you obtain x1. Now, so you do substitution in this way because you can extract arbitrary value, so any value for x sub 3, x sub 4. This means that the system has infinitely many solutions. That is because x3, x2 can be taken arbitrarily. Yeah? Any value in the set of real numbers or even in the set of C. But we are working with real numbers, so let's consider real numbers. Okay, this is even in case that the system has infinitely many solutions, we can use a Gauss elimination to find all of solution. Here, all of solution can be represented in this way. x1 equal 2 minus x4, x2 equal 1 minus x3 plus 4 x4, where 3 except 4 are arbitrarily taken. Yeah? So this means you have many solutions, infinitely many solutions, because x3, x4 can be taken any values. Yeah? Good. Now, and then you may ask, what happens if the system has no solution? Can we use a, can we use a Gauss elimination? Of course, we can use. Let me show you an example. Just in case the system may not have solution, then Gauss elimination lead you to some contradiction, and from this contradiction, you can say the system has no solution. Okay, now we are considering determined systems. So there are 3 equations and 3 unknowns. And then you can write out augmented matrix, you write the coefficient matrix, and then the column B on the right hand side, and you use this slash to distinguish this between 2 block of coefficient matrix and block of the right hand side. But if you are already familiar, you can drop this slash. It's not necessary when you are already familiar with the way, you know. Okay, but now as a beginning, you can use this slash to distinguish between 2 blocks. Eliminate the 2 by either multiply minus 2 over 3 with the first row and add to the second row. Now, then you obtain 0 minus 1 third, 1 third minus 2. And then to eliminate 6, you just multiply minus 2 with the first row and add to the third row. We obtain 0 here, minus 2 here, minus 2 here, 0 here. Okay, now we have to eliminate this minus 2. So I just multiply 6 with the row 2, minus 6 with the row 2, add it here. And you obtain 0, 0, and you obtain 12 here. And you obtain something contradiction, because the last equation here means that 0 equal 0x3 equal 12, means that 0 equal 12 now. This is a contradiction. And this contradiction ending that the system has no solution. Right? Okay. Now look back what we already done here. So we have 3 examples. So this is the last example telling you that there is no solution. So maybe the system have no solution. And this is infinitely many solution, and the form of matrix is actually is not really triangular matrix, because triangular should be square, but this is not square matrix anymore, whatever, but it contains some of triangular. Therefore we need to define exactly the form of the matrix obtained at the end of Gauss elimination. Yeah? So we define the following echelon matrices. Before giving you the definition of echelon matrix, I remind you the notion of zero row. Zero row, that means that the row vectors whose components are on 0. And if one of the components is not 0, then it's called non-zero. Non-zero row, this means that the row is not 0 rows. You know, at least one of the components is not 0, then we call it non-zero rows. So now we have the definition of echelon matrix. So a matrix is called echelon if and only if these 2 conditions are satisfied. The first condition means that all the 0 rows, if any, are on the bottom of the matrix. Yeah. And now consider the non-zero rows. We have the fact that in the non-zero rows, each leading non-zero entry is to the right of the leading non-zero entry in the preceding row. A little bit difficult to understand, but let's look at an example, then you can see immediately what an echelon matrix is. Here, this is an example of an echelon matrix. Here there is only one zero row, so it should be at the bottom. Now it must be at the bottom, and then on the non-zero rows, the leading non-zero entry. Leading means that the first non-zero entry. Now previously all of entries should be zero, and this is the first non-zero entry. Therefore, we call this is leading non-zero entry. Should be to the right of the leading non-zero entry of the preceding rows. This row is preceding of that row. Therefore, the 7 should be to the right of this 2. It can be sitting here, of course, can be sitting here, good, but it cannot be sitting here because it's the same position. It should be to the right, not the same position. And number 2 is leading non-zero entry of this row should be to the right of number 1 here, because the number 1 is leading non-zero rows of this row, preceding the row containing 2 here. Yeah, it's easy, so it forms some kind of step. Yeah, we call this echelon. So the pronunciation you can check. Yeah, echelon. Good. This is and now I want to ask you a question. Maybe I write here on the whiteboard so you can understand. Is an upper triangular matrix echelon? So I write here so that you have some time to think. Is an upper triangular matrix echelon? Tell me. There are two choices, yes or no. Yes or no?
Yes.
Is there any more answer?
No, sir.
No. Good. True. Let me tell you an example. Yeah? Here is an upper triangular. Upper means that the lower part 0. No? So this is upper triangular because the lower part below the main diagonal are 0, but it's not echelon because here you see the leading non-zero entry on this row is the same position as the leading non-zero here. So this is not echelon matrix. If you want to change it to echelon, you have to do one more row operation. So let's do this row 3 minus 2, row 2 replacing to row 3. And the new matrix will be echelon. Because then the last row becomes 0 and the 0 in the bottom is exactly the form of echelon. This is echelon. Echelon. Yeah. So echelon matrix is thick than the upper triangular. Yeah. So okay, but this you have to pay attention now. So the leading non-zero entries on the non-zero rows, the leading non-zero entry is to the right of the leading non-zero entry of preceding rows. Now, this matrix is not echelon because the leading non-zero entry on this non-zero row actually the same position as leading non-zero entry of the preceding row here. If you want to obtain echelon, you have to eliminate this, because we have a chance to eliminate. When still you have a chance to eliminate, then it's not echelon. Yeah? Here there is no more chance. Yeah? You can eliminate no more because it's already zero, and the position is to the right already, so no chance to eliminate anymore. Then it's become echelon. Good. Now we go again to the slide and tell you what happened for. Okay, now look back at the end of Gauss elimination before we do substitution. This own way echelon form. Yeah? That or that exactly echelon form, or that exactly echelon form. Yeah? So the zero rows to the bottom, and on the non-zero rows, the leading non-zero entries is on way to the right of the leading non-zero entry of preceding term. This is to the right of this, and this is to the right of this. Okay, now we have the following notation note on Gauss elimination. At the end of Gauss elimination, before we do the back substitution, then we have an echelon form of the augmented matrix, and then the system has also the echelon form. Yeah? And therefore, we have this form like this. So the zero should be at the bottom of the system, or the matrix means that of the system. And then on the non-zero rows and the non-zero leading term should be to the right, yeah, to the right, so that you can show readily, show backwardly. Yeah. Here, of course, R less than M is number of equation as yeah, at this stage less than or equal to M, of course. And this is leading non-zero coefficient, leading non-zero entry of the end of the echelon matrix. So therefore, all of them are not zero. No? They are leading non-zero entries of non-zero rows. Yeah? So arrange increasingly. Right? So there are three possibilities in which a system may have. The first thing is no solution if this number r less than m, and this b tuner r plus 1 is not zero, so we obtain something contradiction. Yeah, so we obtain some contradiction as the last example that I gave you. So the contradiction means that there is no solution, and then it may have unique solution. It's number r here, number of this equation, the same number of unknowns, and this b tuner r plus 1 if exists, if present, should be zero, so that you obtain 0 equal 0, and then there is no contradiction. Yeah, so you obtain unique solution because you can solve uniquely backwardly. And the last one, as the last and the previous example that I gave you, this may have infinitely many solutions. If this r less than n, and this b tilde r plus 1 of course 0, so that there is no contradiction. Yeah, because if it has contradiction, then it has no solution. Yeah? And what we want to consider is the last case here. So the other case A and B is easy already. Yeah? We can work easily. But now for the last case, C, we want to show to find solution in this case, we have to do the following way. So first, so to obtain solution in this case C, you have to do the following. First, you have to determine the free variables. This means the unknowns which are not leading in any equation. So this is not x1, not xj2, blah blah. So this means xk is free variable if and only if xk is not in the set of these are leading term here. No? So the unknowns which are not leading in any equation, then it is free variable. Then after you choose free variable and then turn the free variables to the other hand side, to the right hand side, and show the rest x1, xj2, blah blah, xjr with respect to the free variables. You know? So we assign arbitrary value for the free variable as x3, x4 that we saw in the last example, and then you compute the remain here x1, xj2, blah blah, xjr just by substitution and with respect to free variable. So look again as what we did with the last thing here. So we choose x3, x4, the free variables, because these two variables are not leading any equation here. So the leading unknowns now x1 and x2. We have to keep this leading equation, leading term here. We have to keep, and then we turn the other x3, x4 to other hand side and solve x1, x2 with respect to x3, x4. So actually, immediately you obtain x2 equal 1 minus x3 plus x4. After you turn these two free variables to the other hand side, you obtain immediately x2, and then substituting x2 to the first equation, you obtain x sub 1. And it's good, right? Because in this case you have infinitely many solutions, because here x3, x4 can be taken arbitrarily, any value. No? Good. This is the way we can do when the system has infinitely many solutions. Now we return to this here. Good. So this is the way that we have to work. We have to do when we want to solve for solution in the case C, that system has infinitely many solutions. Actually, you can uh, you can solve any solution. Let me show you an example now, and I will choose such that it has infinitely many solutions. That is interesting, yeah. So you have to choose some unknowns so that it becomes free variables. But it's easy because that unknown not leading in any equation, yeah. So let me show you an example. Okay, let me return to the whiteboard. So I clear the canvas. I should choose a good system so that it has x1 plus 2 x sub 2 minus x sub 3 plus 3 x4 equal 2, for example. So 2x1 minus x2 plus 2x sub 3 plus x4 equal 1. 3x1 plus x2 plus x3 plus 4x4 equal 3. Okay, now we know how to do this now. So firstly, we write augmented matrix. A tuner is combined by uh, the coefficient matrix first, and then the column. So you can use a slash here, but it's not necessary now because we already has many samples, so you are familiar with this now. If you don't, if you like, you can put a slash here, but I don't like the slash now. But let's begin with that flash. Am I right? Let's check. Okay, it's incorrect now. So 1, 2, minus 1, 3, 2, 2, minus 1, 2, 1, 1, 3, 1, 1, 4, 3. Good. Now do the row operation to eliminate this 0 here, 0 here, 0 here. Now, so to eliminate this 0, you should do this row 2 minus 2 row 1, replacing to the row 2. So the first row is pivot, yeah. So keep this unchanged, and here you obtain 0, minus 1, minus 4 is minus 5. Am I right? 2 plus 2 is 0, yeah, because minus minus plus 1 minus 6 is minus 5. Am I right? And 1 minus is minus 3. Yeah. So this means that we multiply the whole row with minus 2 and we add to this second here. Yeah. Let me check again. So minus 2 is here is minus 5 minus so why is 0? Well, let me check this again. There's something wrong with this. Yeah, let me check this again. So this will be 4. So if we so 2 minus minus plus is 4. Yeah. And then 1 minus 6 is minus 5, and 1 minus 4 is what? And then row 3 minus 3 row 1 here okay, I made some mistake here, replace to row here, replace to row 2, not row 3, and here row 3 now. Row 3 minus 3 row 1 replacing to row 3. Now you obtain 0 here. 1 minus 6 is minus 5. 1 plus 3 is 4. 4 minus 9 is minus 5. 3 minus 6 is minus 3. If you like, you can make a slash here. And now you just multiply minus 1 here and add this here. It's easy now, right? 0 minus 5, 4 minus 5. And here you add row 3 minus row 2, replacing to row 3. So we obtain 0, 0, 0, 0. And this is echelon form already. So 0 rows on the bottom, and on the non-zero row, the leading non-zero entry is to the right of the leading non-zero entry of the previous row, preceding row. So now you can show the system. This is x1 plus 2x2 minus x3 plus 3x4 equal 2, and minus 5 x2 plus 4 x3 minus 5 x4 equal minus 3. So we choose x3 x4 which are not leading any equation, so we choose these free variables. So we obtain the following by substitution. So x2 equal minus 3 minus 4x3 plus 5x4 over 5. Yeah? Over minus 5, so this will be my plus and minus here. Right? So you turn to 1 and divide by 5. Good. And then substituting to obtain x1, so you have to please for me. And we finish for all x3, x4, say in R, if we are considered in the set of real number. You can x3, x4, you can be taking any value, so you have infinitely many solutions in this case, because x3, x4 can be taken any value. Okay, this is the end. We already the time's already up, so we have to finish it here. And of course, I will close the room. Before doing that, I take no, I have to download the attendance list first, before I close. Good. So, thank you for joining us, and see you next time. Bye bye.